Okay, from the first part, we know that the kinetics process is the time-dependent state function change process. And how fast or how slow it is were determined by the driving force and also the inertia or mobility of the systems. And the other important part will be if your kinetics process is not not a one-step process. If it is like involve two or more steps, you need to figure out which steps is the rate determine or limitation steps. That's quite important. So let's move to the second part. It's the equilibrium state versus the steady state. So what is equilibrium state and what is steady state? We have some definitions shown in our textbook. Equilibrium state can be considered as the F means the state function can be temperature, pressure, energy, and so on. So the partial F, partial T equals to 0, which means that the state function does not change with time. And also, there's no driving force involved in these systems, and um, we call it as an equilibrium condition or equilibrium state. For example, there's no any chemical potential gradient, which means that there's no chemical potential difference inside these systems. That no driving force, so that will lead no mass flux, no mass transpose. So this is the equilibrium condition. Also, if there's no temperature gradient, which means that there's no temperature difference inside these material systems, then that won't lead any heat flow. Heat flow equals to 0. So these systems are under equilibrium state or equilibrium conditions. And what is steady state? What's the difference between steady state and equilibrium conditions? The steady state also, we find that the state function f also does not change with time. So partial f, partial t equals to 0. But we do have, or we do exist, the driving force acting or apply on our systems. For example, like due to we have the chemical potential gradient, so that have a constant, that lead the constant mass flux. And or we do have a temperature gradient, temperature difference inside our systems. This will lead the heat flow passing through interesting materials. So we have a constant mass flux or heat flow exist on our systems under applied driving force. This we call the steady state. I think the most important part will be we have to have a driving force, and this is the constant driving force. So that will lead the constant flux, constant and constant. So the most important part is constant driving force, then lead the constant mass flux or heat flow. 所以，在 steady state 这里的话，它跟平衡状态不一样的地方，就是它有一个 driving force，那它就会导致说，因为你有力嘛，所以你就会引发这个 flux，也就是不管是mass flux、heat flow 或者是 current，然后 passing your materials，但在 steady state，因为它是steady state 是稳定的流动状态，所以它不单纯只是一个 driving force，它还是一个 constant 的 driving force，它是一个固定的 driving force，所以它也会导致于你的 flow，就是你的 flux 是固定的，所以它可以是固定的原子的移动、热的流动，或者是电子或是电流的。 then the other is as long as you remove the driving force, then the flow will go from the non-equilibrium state to an equilibrium state. So, which is also the kinetics process we previously mentioned about, right? You need to external driving force to push the system out of equilibrium state. Then the path it choose to back to or move to equilibrium condition. This process is we call a kinetics path. And um, the other, some people probably will ask, Professor, how about if our driving force is not a constant driving force? It changes with time, which means that sometimes it's larger, sometimes it's smaller, which means that our driving force change with time. So what happened that will lead the non-steady state, 非稳态, and you will have a time-dependent differential equation. So this is just for your reference. So now I'm going to show you there are two steady state flow process. The first one will be the steady state heat flow process. And the second one will be the steady state mass transport or mass flow process. And also I also introduced the non-steady case for your reference. Okay, so let's move to the steady state heat flow process. And what we have here is actually we introduced this case before, so I move like faster. So what we have here is we have a metal bar, and we use the temperature. We use a thermocouple to measure the temperature along this metal bar. And this thermocouple, we just ignore the heat capacity of this thermocouple, and just which the reason here is, which means that the exist all of this thermocouple does not change the temperature gradient, temperature distribution along this metal bar. So we assume that we just ignore the heat capacity of this thermocouple. And the only function of this thermocouple is just, we just use it to measure the temperature distribution along this metal bar. And we put the heat reservoir to provide the heat, and we put the cold reservoir to absorb the heat. And we tune some specific conditions to allow the heat in equals to heat out. The amount of heat inside this material, flow inside this materials equals to the amount of heat flow outside this material systems. So the metal bar just serve as a heat transporter. This metal bar does not store any heat. And then we use a thermocouple to measure the temperature gradient or temperature distribution along this metal bar. We find that temperature gradient or temperature distribution show like this. On your left-handed side, which close to the heat reservoir, have a higher temperature TH than on your right-hand side TC. And we also find that due to the heat Q in equals to Q out, there's no any heat stored inside these metal materials. So they find that the temperature distribution, this distribution does not change with time, which means that when you measure the temperature at like 1 hour after, the temperature distribution show like this. But like 1 day after also show like this. And 1 week after also show like this, which means that the partial T, capital T, partial T, partial small t, does not change with time. The state function, temperature, does not change with time. So the partial T versus partial T equals 0, which means that the temperature distribution does not change with time, but we do have a temperature gradient temperature gradient not equals to 0, we do have the temperature difference of temperature gradient inside our material systems. So under this situation, this system do have a steady state heat flow process. So some people probably will question, Professor, are you sure this system, the heat flow inside this system can be considered as a steady state heat flow process? So we just grab the criteria shown in previous slide, how to define this is to define the system reach the steady state. We just check whether the system fit each criteria or not. For in previous slide here, let's conditions. For previous slide, we said that the state function does not change with time if it is steady state. So the temperature does not change with time. So yes. And the second criteria mentioned in previous slide, talking about that as long as we remove the driving force. Oh, sorry. The second choice is second criteria is we have a driving force, and which lead the constant driving force. So we do have a driving force, temperature gradient, and also really lead the heat flux. So also satisfy the criteria too. And the third one in previous slide actually is when you remove the driving force, the system will go from non-equilibrium state to equilibrium state. So let's check. If we remove the red reservoir and cold reservoir, then the system finally, I believe, will move to constant temperature. So the constant temperature, no temperature gradient, no driving force, the system go to equilibrium condition. So after checking these three criteria for steady state, we can say the system we are talking about is a steady state heat flow process. So this is a steady state heat flow process, right? So let's give you another example. Yes, steady state or non-steady state in mass transport. So what we have here is, before we talking about the detail, we need to have like a quick background review here. We talk more about mass transport in solid materials, and also talk about the mass conservation law, which is quite important in mass transport. So what we have here is we just focus on our interesting cubic here. And we have some atoms passing through from your left-handed side toward to your right-handed side. And based on, because we have atomic atoms moves along x-axis and move from left-handed side toward to right-handed side. So we also define the diameter of this cubic we are interested in is the length is delta x, and this is area we call A. And because we have atomic flux, so we call that Jx to represent the atom's atomic flux flow inside this box, this cubic. And we also use J flux x plus delta x to represent the atom's atomic flux flow outside this cubic. Based on the mass conservation law, 就是质量守恒定律, the mass change of or inside this cubic, we use a partial m mass, partial t is a mass change rate of inside this cubic equals to the atoms flow inside this box minus flow outside this box, which equals to the atoms remaining inside this box, right? So we use the partial m partial t equals to jxa minus jx plus delta xa. And then we also equals to what? In order to, because mass is hard to measure, right? So we are quite difficult to measure the the specific mass for specific atoms. So we prefer to convert these parameters to concentration, something like that. So that would be easy to know the concentration for specific materials. So we partial m partial t is a mass change rate, can be rewritten as partial c. Partial t is a concentration change rate. Concentration is a mass per unit volume. So mass is mass per unit volume. So I times the volume on your right-hand side. So times A times delta X. So we also have the partial M, partial T. So now I have this like equations. So this is derived from mass conservation law. So I just divided because I delete the A, they have together. So I just rewritten this equation. These equations can be rewritten as partial C, partial D is concentration change rate of your interesting diffusion atoms. Partial C, partial T. And I take the delta X to the right-handed side, which means that divided by delta X. The flux divided by delta X is a gradient. So we have the minus flux gradient. Okay, so here we use a minus because the left-hand side is the Jx minus the Jx plus delta X, this minus this one. But we familiar with use the later one to minus the earlier one. So we will put the minus here. Okay, so based on the mass conservation law, we get this equation, and this equation actually is quite famous. Okay, and next we are going to replace the flux one based on the fixed first law. The fixed first law tells us the flux equals to negative diffusivity times the concentration gradient. So I rewritten this equation. So based on the combining the mass conservation law and fixed first law, we derive these equations. So if the systems to describe the mass transport phenomenon along our solid materials. So for steady state, what steady state means? Means that we do have a constant mass transport under constant driving force, which means that partial C, partial T, you have a constant mass transport under the constant driving force. So partial C, partial T equals to 0. So this equals to 0. But we do have a concentration gradient. So based on these results, you can focus on here. We do have a concentration gradient, right? So, but this equals to 0. So let's tell you that the more easier way is the partial. Tell you that the inside here, we can take the diffusivity. If the diffusivity equals to constant, 是常数的话, we can take it out. Then we can have the diffusivity outside, right? And the concentration, take the second gradient respect to x equals to 0. So this is how and as long as you solve those equations, you can get how the concentration of diffusing atoms change with locations because it is steady state. Partial C, partial T equals to 0, which means that the concentration profile does not change with time. Not change with time, but change with location. So based on this equation, you can get how it change with locations. But if we back to original equations we have, if it's non-steady state, which means that we do have a time varying mass flow due to time-dependent driving force acting on our materials. So partial C, partial T, the concentration profile does change with time. So this is not equals to 0. So you cannot simplify this differentiation equation. You need to solve it. So based on here, we can use this and this. So also assume diffusivity equals to constant, take it outside. So we have right-hand side, we have the concentration change rate. On your right-hand side, diffusivity has been taken outside. We also have the concentration, take the second gradient, secondary gradient or secondary uh, deviation respect to x. So as long as we solve this differentiation equation, then you can know that how the concentration profile of diffusing atoms change with location x and time. So this is also the mass transport in solid materials. Okay. So I'm going to give you a quick summary for equilibrium state and steady state. Regarding talking about the thermodynamic equilibrium state, our state we do not have driving force acting on these materials, so that leads there's no state function change. The state function does not change with time. All this is defined by thermodynamics law, and no driving force, no net flux as well. And regarding to the steady state, we are interested in kinetics. We do have a constant driving force acting or apply on our material system that will lead the constant flow passing through. And regarding those to the state function, the state function does not change as with time, but we do have the flow passing through your materials. And in order to answer how fast or how slow it is, we assume local equilibrium conditions at any specific locations inside our materials. And concentration determined by time-independent diffusion equation, which means that because it's steady state, so in order to know the concentration profile, that depending on that will change. The concentration profile does change with location, but not change with time because concentration does not change with time because it's steady state. The state function does not change with time, right? The concentration profile always look like the same over time. But however, when we move to the non-steady state, which means that we do have time varying or time dependent driving force acting on our materials, that will lead the time dependent flux passing through our materials. So as under these situations, you also can know the concentration profile, how the concentration profile change with location and time after solving this uh, differentiation equation with two variable. And in order to simplify the differential equation, we assume that D equals to constant. Okay. And some people probably at this moment you already have some idea what's the difference between these three states, but may have some questions. Professor, under what type of system the system would tend to go to equilibrium state or steady state? Are there any hint or can I, based on what conditions to know that? So I give you some examples here, probably will help you to determine whether the systems move to steady state or equilibrium conditions. So in your textbook, they highlight that if we have homogeneous boundary conditions, the system will go to equilibrium state irreversibly. So what is a homogeneous boundary condition? Which means that if there's no external driving force, the system finally will go to thermodynamic equilibrium condition. So I'll give you an example. In the beginning, we have a metal bar, and I put heat reservoir on the two end of this metal bar, and the temperature are the same TH. So this two heat reservoir will provide the heat flow to this metal bar. So finally, the temperature distribution on this metal bar will change or increase from T bar to TH. But if you measure them, any TH, they have a constant TH temperature along this metal bar, which means that the system reach the equilibrium condition. Why? Because we do not have the external driving force, right? So this is homogeneous boundary condition because we don't have the external driving force. We do not have any temperature gradient along this metal bar. So that leads the system go to equilibrium condition, irreversible. And however, if we do have the inhomogeneous boundary condition, the system have chance to go irreversibly to steady state. What this means, inhomogeneous. Compared to homogeneous, we can expect that there's an external driving force. So for this case, which means that I put the heat reservoir on your left-hand side and the other cold reservoir on your right-hand side on this metal bar. So that will that will lead the heat flux due to this external heat driving force gradient, temperature gradient. So as long as the Q in equals to Q out, the system will reach steady state heat flow process, which means a steady state. Then also when you measure the state function T, we do have a temperature gradient, temperature distribution along this metal bar, and this distribution does not change with time. So as long as you have external driving force, then the system finally will have chance to move to steady state. Otherwise, like this case, finally the system will go to thermodynamic equilibrium condition. So in order to determine where your systems go, I think figure out, are there any driving force acting on your material system is the key point. Okay, so we finish the second part, the difference between the equilibrium and steady state. And for the steady state, don't forget the steady state means that the state function does not change with time, but we do have a driving force acting on our material system. And as long as the state function does not change with time, so people always curious about what's the concentration, temperature, or electrical potential distribution along these materials. So as long as you can successfully solve this differentiation equation or any equations, you have chance to know how the concentration change with location.